Welcome students to another video lecture with Mr. Connect. This video lecture is on 11.3 where we're going to learn about some polygons, and you're going to need to reference your 11.2 note to work through this lesson. So go ahead and pause here, copy what you see, and make sure you have 11.2 somewhere ready to go to work with. Okay, welcome back, students. So in our lesson today, we are trying to find a way to name polygons, which will be a little table we'll write down about. And we're also trying to find a sum of their interior angles. So we're going to have two focuses here, finding out how to name polygons, as well as having to find out what the sum of their interior angles is. It's key you understand that a polygon is any closed figure formed by three or more line segments. Remember, a line segment is just a line with no arrows on it because that ends. So we're going to see how polygons can be used in math problems. So I'm going to jump 2 slides ahead. So the first one you're going to copy down is this classifying polygons, so you understand some names of polygons. And then also notice I have a squiggly line cutting off these captions, so make sure you're doing this from top to bottom on your note. But we're also going to talk about how we're about to create the interior angle of a polygon formula, and I'm going to show it visually how it's actually created. So pause here and copy down what you see. Okay, welcome back. So I think you can understand classifying polygons, and I think many of you know what triangles are. The prefix quad we've learned means 4, so that's any 4-sided figure. I drew a rectangle, but I could have just as well drawn a parallelogram. So remember, quadrilateral is any 4-sided figure. Pentagon is anything with 5. Hex is 6. Heptagon is 7. Octagon is 8. Nonagon is 9. Decagon is 10. And it does actually keep on going. I just didn't want to cramp your hand too far. And that's as much as I'm really going to ask you to look for. So now, the more important part. We're going to learn that there's a formula to find the interior angle of any polygon. And in 11.2, we've already learned about the interior angles of a triangle. And all of this formula is based off of is that triangle formula and recognizing a pattern that occurs as we keep on going from one shape to another. So what I need you to do is open up your 11.2 note and check for me, what do the interior angles of a triangle always add up to? I'll pause here and go ahead and check. Excellent. So as you checked the interior part of a polygon for the triangle, so checking your 11.2 note, you likely learned that the interior angles add up to 180 degrees. And what we're going to try and do here is show a comparison of interior angles, I'm going to abbreviate it IA, and number of sides, and we're going to use a letter, N. So the N stands for number of sides. And again, we're trying to figure out a pattern that occurs as we start cutting each shape up into more and more triangles, the one we actually knew to start with. So N is always going to stand for number of sides in this lesson. So how many sides does this triangle have? Yeah, you're right, it's 3. Yeah, we could probably go ahead and start counting the number of sides we have for these things. And we're going to hopefully start seeing a pattern. So our quadrilateral has 4. Our pentagon has 5. Our hexagon has 6. And this is a heptagon, which actually has 7. And I'm just changing the colors to help visually see this. So now, we're going to try and cut the quadrilateral into triangles. So if we were to cut our square into triangles, we would be able to create how many triangles inside of this square? Yeah, hopefully you see 2. And since we know that the interior angle of any triangle is 180, and there are 2 triangles inside of this quadrilateral, what's 2 times 180? Yeah, so the inside of any quadrilateral always adds up to 360 degrees. Okay, so now we're on to the pentagon. How many triangles can we cut the pentagon up to? Let's find out. 1, 2, Oh, I don't think I can go any further. If we tried to make other ones like this, we'd actually be cutting through the other triangles that are already there. So when we do this activity, you're literally only trying to create triangles from a single corner without going over any other line. And I know my smartboard didn't do a good job of showing not going over any other line, but how many triangles did we create inside of a pentagon? Yeah, it's 3. So we have to do 3 times 180. So that gets us 540 degrees. So the interior angles of any pentagon are 540 degrees. I should probably label my 2 triangles there. Okay. Okay, now we're moving on to a hexagon. I'm going to ask you try and do the septagon on your own. So really pay attention to how we do this hexagon. I choose one corner to always start my lines from. So I can make 1, 2, and 3 lines in there, which creates how many different triangles? 4. Oh, and what's 4 times 180? Yeah, it's 720 degrees. So right now, we have enough evidence where you may start being able to create the pattern. We know that this hexagon has 6 sides, and it ends up with 4 triangles inside of it. The pentagon has 5 sides, and ends up with 3 triangles. So can you begin to think of a relationship between the number of sides and the number of triangles that end up in the shape? So go ahead and pause here and copy down, try and create as many triangles as you can without overlapping them inside of the heptagon. Awesome job. So you may, just like me, always be choosing that one corner, 1 triangle, 2 triangles, 3 triangles, 4 and 5. Huh. Have you figured out the pattern yet? So we'd have to do 5 times 180, and yeah, that's 900 degrees for any interior angles of a heptagon. And we had 7 sides, and we ended up with 5 triangles. 6 sides, 4 triangles. 5 sides, 3 triangles. 4 sides, 2 triangles. 3 sides, 1 triangle. What's the formula if you knew the number of sides of, say, a 12-sided figure? How could we figure out how many the interior angles would sum up to? Did you figure it out? There's a formula. And it's right there. The formula of any interior angle is you take the n, which again, remember, stands for the number of sides, and you subtract 2 and multiply by 180. That's what we kept on doing every single time. So that's how we create the sum of interior angles formula. It always equals the number of sides minus 2 times 180. So let's go ahead and see how this will be used in our problems. First problem we have is find the sum of the measure of interior angles of a nonagon. So I would love it if you paused it here and gave it a try. Okay, welcome back. So I am always going to write the sum of interior angles. So I'm going to call this Cia. And really it's just one variable. We're going to connect it all together. And I made it up from sum of interior angles. Always equals n minus 2 times 180. Notice we're using a formula, so I wrote the formula down. A nonagon has 9 sides, so we know n equals 9. All we do is substitute into our formula, and you know it, solve, and we can get our answer. N minus 2 gets us 7, and 7 times 180. Give me 1 second as we actually do that in my head here. That's going to get us 1240. I apologize. I did my math wrong. I should do it on the side rather than have to make a whole new video lecture where I messed it up. 7 times 8 is actually 56. See, I already messed this up. I'm glad I double-checked. Who got 1,260 degrees? You were all about to pick on me. But we just found out that the interior angle of any nonagon always adds up to 1,260 degrees. The next way these problems could happen is now we're going to try and figure out what each angle, and the key word is each angle, is inside of the nonagon. So go ahead and write this down, and as you do that, start thinking about what math we're going to have to do with what we know the entire sum of angles is when we now know that there are 9 angles in a nonagon and we want to know the measurement of each. Okay, so we know the sum of an interior angles of a nonagon equals 1,260 degrees. Now we know that there are 9 angles in a nonagon. And if we want to find each, you're right, we have to do 1,260 divided by 9. And when we do that, we actually find that each angle of a nonagon is going to be 140 degrees. So each angle of our nonagon will be, if they are all equal, like the problem said, it did have to say equal, each angle of a nonagon would be 140 degrees. So I'm hoping these math problems are not too complex. So I'm going to jump ahead here. We're going to get to example 2, and I'm just going to ask you to name example 2. So go ahead and name that nonagon, or sorry, that polygon. It's not a nonagon. I should learn to count. Awesome. We'll get our answer in class. And then the last one is more of the algebra we're going to use for this formula. So I'd love you to write example 3 down, and I'd love you to actually try to solve example 3 using this interior angle of a polygon formula. It's going to be really similar to the example I just showed, part 2 of the nonagon. So that's it for 11.3 on polygons. I hope everything goes well. Please remember to keep on writing your questions down in the question column and come see me if you need any help.